We developed a software method, a computer program that uses 3D facial imaging to classify people to a genetic disease. The algorithm was developed by a former grad student of mine, David Aponte, and this is work that was done in close collaboration with François Bernier, who is the director of UCalgary, as well as colleagues around the world. We are able to classify a large range of genetic diseases, and so it has great potential for use as a low-cost screening tool that allows clinicians potentially to screen people for genetic diseases. So the partnership started in a funny way. I was going on a trip. I was at the Calgary airport.
My name is Ira Lahi. I'm the founder and president of Rapid 3D. I was going through the security line and I heard somebody ask me if that was a 3D scanner that I had with me.
Is that a 3D scanner? What are you going to be doing with that? Ira, who was the CEO of Rapid 3D, was the person carrying this equipment.
We struck up a conversation and we agreed to touch base once we returned back to Calgary, and that was the kind of the beginning of it.
In many ways, it's a great example of university business collaboration. The result of this partnership is this beautiful camera that has been created. And the next stage in the evolution of this work is to see if we can get this camera to work within a clinical setting. If it works within a clinical setting, then the sky's the limit as to what can be done with this technology.
The main part of the challenge was the existing system wasn't an instant capture system. It had 3 scanning devices, and they would capture 1, 2, 3. And so any motion would cause a lot of issues. And so he needed an instant capture type of a system. The initial prototype, it had 10 by 8 foot footprint. The reason being is we didn't know the end quality result we would get. Based on the results and some further testing, we found that we could reduce the footprint quite a bit. So the system that we have now, our version 2 system, is about a 5 by 5 foot footprint. That's the main benefit of making it smaller. It's strictly space. Think about when you go into your doctor's office, the room is tiny and there's a lot of stuff already in there. So the smaller the system can be made, the larger scale implementation would be a little bit easier.
It's very interesting and exciting for us to be able to participate in something that is actually going to make a difference and matter to not only the children, but the parents and the clinicians and doctors that are utilizing the machine learning technology that Benedict and his team have built and are implementing. Benedict and his team have been very open, very communicative, and really a lot of fun to work with. I think at the end of the day, we've got something that works very well for their application, but it's also given us the confidence and motivation to continue to develop other iterations that could potentially be, like I said, more portable or smaller.
This project in general is a component of the Child Precision Health theme, Listen One Child, Every Child. One of the goals of that theme is to create new ways to better diagnose rare and chronic diseases. And so this is one of many such initiatives that we're pursuing within One Child, Every Child to improve health outcomes for children in Canada.